Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn how to solve a linear system using a strategy called substitution. This is one of two different strategies we will learn as part of this unit, and both of them will involve us learning how to find a point of intersection between two lines using algebra. This lesson will learn a strategy called, like I mentioned, substitution. And to start off, I invite you to go ahead and find the point of intersection between these two linear relations. You can see they're already in slope-intercept form, and do that by graphing. Pause the video here and go do that. Well, if you had chosen to do this, there's actually two approaches, even if you were to choose the graphing strategy in general. One of them is by hand, and of course, the other one is using technology. Let's look at how you might do this by hand first. First of all, you definitely would need a pair of axes. And notice my y-axis goes from -2 to 5. And I know that it's got to go from -2 to 5 because I'm looking at these two linear relations right here. I can see that for this linear relation, the y-intercept is -2. And so I will definitely need to go as far down on the y-axis as -2 because I'll need to put the y-intercept, a coordinate, right here at 0 and -2. And I knew that I had to go up as high as 5 because the y-intercept for the other linear relation, very similarly, which I'll get to in a bit, is +5. But let's go back to this one for a second. Let's start to graph it out. The first step to graphing a linear relation in slope-intercept form is what I've already done. Plot the y-intercept, and you can figure out which number is the y-intercept just by looking at which one does not have the x beside it. And so in this case, it's -2. Now, from this point, we have to go up by the rise and to the right by the run. And what do I mean by that? Well, I'm looking at the other number here, the number that actually is being multiplied by x. In this case, that's 3. That number represents the slope, or how steep the line is. The slope tells us how much we have to rise. So we have to go up by 3 units. When you rise, you go up every time you go across by the denominator. In this case, because this is just a whole number can always be turned into a fraction just by making it over 1. And so this is 3 over 1. The rise is 3. The run is 1. Whatever the sign of this number is, we'll just assign it to the top number for now. That way we can keep the bottom number always at +1, or always a positive number. We're always going to the right. Okay, so from here, we're going to rise by 3, 1, 2, 3, and we're going to run to the right by 1. And that right here is where we will draw our next point. From this point, we can repeat those steps up by 3, across by 1 to draw our next point. And I think I'm out of room here. I think I'll end up like off my graph. So I think at this point, I'm going to stop and I'll just draw a straight line cutting through all 3 of these points. So this right here is the linear relation y equals 3x minus 2. If you weren't able to draw this by hand, I invite you to pause the video here and using the steps that we just did, graph this line on the same set of axes. Hopefully you recognize that our first step was to evaluate which of these two numbers was the slope and which was the y-intercept. Of course, the +5 is the y-intercept and -2 over 1 is the slope. And so we're going to start off with our y-intercept at 0, 5, which is right over here. And now we're going to rise by -2. So how do you rise by a negative number? Of course, you fall, go down by 2, and then still to the right by 1, because the run, we like to keep that as positive. And that's where we'll draw our next point, and we'll just keep going in that pattern. Down by 2, across by 1. We actually do have some more space, so we'll just keep going. Down by 2, across by 1, keep our point there. And I think that's enough work. We can just connect these with a straight line. And there we go, folks. We have both of our lines graphed by hand. Now we just have to find the point of intersection. And we can see that they intersect right over here. Now, because my lines were graphed by hand, this is a little, well, sketchy is probably the best word to use here. The point looks like it's around 1.5, and then the y value looks like it's around 2. So that would be my best guess at this point. So you can see already the limitations of finding a point of intersection by hand. If it's not exact, and I don't know if this is exact, If it doesn't fall exactly on one of the grid lines, it's tough to know what those x and y values are. Now, if we were to use technology, we could just graph those two lines, and then we can usually just use the technology. In this case, I'm using Desmos to just click on that point of intersection right there, and it'll tell me the exact coordinates. And it looks like I was off by just a little bit. It's actually 1.4 and 2.2. So this just illustrates why we might need to know how to solve a pair of linear systems without using graphing at all. Both of these strategies, although even the strategy by hand was inaccurate, and the one using technology, well, I needed to have a graphing calculator or a computer near me. Today we're going to learn how to avoid those pitfalls. So we're going to solve the exact same point of intersection, the exact same linear system, but we're going to use a strategy now called substitution, which you don't know quite yet. So I'm not going to ask you to tackle this by yourself until we've gone through it a little bit. This problem, like we just saw, it can be solved graphically. If we do it by hand, it's going to be inaccurate. And instead of saying to ourselves, okay, well, I'll just use a graphing technology, I'll just use Desmos or whatever, instead of increasing our reliance on technology, let's try to do this algebraically. Using algebra, we can look at these and say, well, I know that they're going to cross at some point. And at that point, the x values will be the same and the y values will be the same. And if the y values are going to be the same, that kind of means that the y value from this relation is the same. It has the exact same value as the y value from this relation. And if that's true, I can replace this variable y with what it's equal to, which is 3x minus 2. And I can do the same thing on the right side. I can replace y with negative 2x plus 5. And the reason I would do such a thing is now I have an equation. And what do you notice about this equation? It's a little tricky to pick this up. But there's actually only one variable here. There's only x. I know there's two of them. There's only one type of variable. And when we have an equation that only has one variable, it's usually solvable. So all we have to do to solve it is isolate that variable. So let's move all of our x's to the left. So I see a term with x over here. Let's add 2x from this to the right side, and that will do the opposite of subtracting 2x, so that will cancel it out. And we have to do the same thing to the left side. Now let's move the numerical term over. So let's add 2 to this side, and that will get rid of the negative 2. And if we add 2 to the other side, now we end up with 3x plus 2x is 5x, and 5 plus 2 is 7. Now finally, all we have to do is divide both sides by 5 to get rid of that coefficient of x. And 7 divided by 5 gives us 1.4. Hey, look at that. That was the exact value of x that we found using technology before. Now, how do we find the y value? Well, we actually have two equations here. And we know that when x is 1.4, we can find y in either one. So let's put it into the first, the red one here first. So 3 times 1.4 is 4.2. And 4.2 minus 2 is 2.2. And that was our y value, wasn't it? Would that work if we didn't pick the red equation? I'll invite you to pause here and see if we get the same answer with the blue equation or not. Well, hopefully you did see that, yes, in fact, when we plug in 1.4, 1.4 times negative 2 is negative 2.8, plus 5 is 2.2. So the point of intersection, we found it algebraically without using a graphing technology, without having to use a graph by hand, which can be inaccurate. We solved it algebraically and found the point of intersection was 1.4 and 2.2. So what do we learn here? To solve a linear system, and remember, a linear system is a pair of equations. To do that by substitution means to substitute a variable in one equation. So for example, if we have an equation like this and like that, that is a pair of equations. And here are all the steps with this example to solve a linear system by substitution. Step 1 is to choose one of the variables in one of the equations. So I'm going to choose this one. This is equation number 1. And I'm going to choose one variable and isolate it. Let's isolate y. Okay, no particular reason. If you had chosen to isolate x, you would end up with the right answer no matter what. But I'm choosing to isolate y. So I'm subtracting x on both sides, and now I have 80 minus x. That's the value of y. Well, if this is the value of y, if y is equal to this expression, well, I have another equation here that has a y in it. Now what I have to do is substitute this expression exactly here where I see y, substituted in the other equation with the expression it's equal to. So I'm going to replace y, and whenever we replace a variable, we always put brackets around it first. Now that I've replaced it, it's time to expand and simplify this expression. So this really doesn't need anything, but now that I have brackets, I have to multiply negative 40, the coefficient, by each of the terms in the brackets. So negative 40 times 80 is negative 3,200, and negative 40 times negative x is positive 40x. Now, of course, expand and simplify, so we do have to combine our like terms. We've got 30x and 40x here. That makes 70x. And now, step 4, we isolate x. Just like in our previous example, we saw that whenever we have an equation with only one type of variable, we can always just isolate that variable to solve it. So let's isolate for x here by adding 3,200 to both sides and then dividing both sides by 70. That tells us that x is 47. Now what's y? Well, I have an equation here that tells me the value of y if I know the value of x. So I'm going to solve for y just by taking that equation and again substituting 47 for x. 80 minus 47 is 33. So x is 47 and y is 33. That is the point of intersection, but our last step is actually just to double check our solution. And we can do that using the other equation here. So 30x minus 40y equals 90. Is this true if x is 47 and y is 33? If I plug those numbers in, I actually do get 30 times 47 minus 40 times 33. I did that all at once. I actually did get 90. And so yes, the point of intersection is at 47 and 33. So when we need to solve linear systems, we should never rely on graphing because graphing either means we need technology or are inaccurate hand sketches. It only works when the x and y values fall exactly on the grid lines. And even then, how can you be sure that it's exactly there? To solve a linear system using substitution instead, which is far more accurate and accessible, first, like we said, isolate one of the variables in one of the equations, substitute that expression into the other equation, and then expand and simplify and isolate that unknown variable. Once you've found it, solve for the other variable by using the other equation, and then check your solution at the end. In this example, to raise some money for their arts program, some grade 10 students held an art show and they charged these prices. At the end, they counted up and sold 144 tickets and made $447. How many students attended this and how many adults? Well, to answer this question first, this is actually a linear systems question, and we need two equations for a linear systems question. There are a few relationships already happening here that we have to sort of parse through, and they're not given to us. So that makes this question a little bit difficult. Pause the video here and see if you can come up with two equations that might be representative in this situation. Well, first of all, to make an equation, we have to sort of identify what are the variables here. What are the values that are unknown? And the two questions give us that clue, right? How many students attended? So that is going to be one of our variables. Let's say S for the number of students, and how many adults. So let's use A for the number of adults. If we add those together, we know that in total there were 144 tickets sold. So the number of students plus the number of adults must equal 144. We also know that the students made $447. So what does that mean? That means that if you take the number of students, whatever that number is, To find out how much money you made from the students, you have to multiply that by the price per student, so times 2. To find out the amount of money you made from the adults, you take the number of adults and you multiply that by 5. And when you add those two together, the amount of money you made from the students plus the amount of money you made from the adults, you should get $447. So these are our two equations. Now let's see if we can use these to solve this linear system. Pause the video here and see if you can take the rest of the steps yourself if you haven't already. Well, our first step is always to, like I mentioned, choose one equation and isolate one of the variables. I'm going to isolate the number of adults. I'm going to isolate A. So in this case, this will turn into 144 minus S. And I'm going to take that expression and I'm going to replace A in the other equation with this exact expression. So this will turn into 2S plus 5 times 144 minus S equals 447. And there we go. We already have an equation with only one variable, and that variable is S. Now it's time to expand and simplify. So 5 times 144 and 5 times negative S. Collect our like terms, 2S and negative 5S, and isolate that S. So let's subtract 720 from both sides and divide both sides by negative 3. That tells us that S equals 91. What does that mean? The number of student tickets sold is 91. Well, if we want to know how many adults attended, if we know that 91 of the 144 tickets were sold to students, the remainder must be sold to the adults. So we could just take 144 and subtract 91, which is exactly what we would do if we took this equation and replaced S with 91. 144 minus 91 gives us 53 adults tickets sold. Let's double check our answer just by using the second equation that we came up with. So here we have 2S plus 5A equals 447. If S is 91 and A is 53, if we evaluate this in our calculator, we will in fact get 447. So 91 students attended, and so did 53 adults. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice question solutions, handouts, and more on our storefront. Thanks and have a great day.